We will use this applet to illustrate important features of projectile motion. We will start by launching this object directly up with an initial velocity of 60 meters per second. So for this first simulation, we will just be looking at linear motion, which we have already covered. It is linear motion with constant acceleration. The acceleration of this particle will be in the downwards direction. It will have a magnitude of 9.81 meters per second squared. So we've already covered this. This is linear motion with constant acceleration. As long as the object is near the surface of the Earth, the acceleration will be 9.81 meters per second squared, vertically down. So you can see the velocity vector decreasing by 9.81 meters per second each second until it gets to 0. Then it changes direction and it increases by 9.81 meters per second each second. Now I've changed the launch angle, so we will no longer be dealing with uniform linear motion. The object will move in some curved path. If there was no gravity or no forces, as soon as the object leaves the launch pad, it will continue on with the constant velocity. So it will move in a straight line with a constant speed of 55 meters per second. This is the speed it will have. Well, this is the velocity it will have immediately after it is launched. So if there are no forces on it immediately after it's launched, by Newton's first law, no forces means constant velocity, which is constant speed in a straight line with the velocity it had immediately after it's launched. However, we're launching this object near the surface of the Earth at an angle of 60 degrees to the horizontal. So we have the force of gravity, or the weight of the object. And that means we will have an acceleration. If we have a force, we have an acceleration by F equals ma. So the only force acting on this object when it leaves the launch pad will be the force of gravity, and that's equal to m, the mass, times g, where g is the acceleration due to gravity. So this object will have an acceleration of g, 9.81 meters per second squared, vertically down. So that constant acceleration will be acting. Now let's launch this and look at the components of the velocity vector. Unfortunately, the velocity vector is not shown in this applet. I'll have to indicate it myself soon. Let's see that again. Notice that the horizontal component remains constant. It doesn't change direction, and its magnitude stays the same. Of course, the vertical component changes magnitude, and it changes direction. Here is a snapshot of the motion of the object in mid-flight. The horizontal component of the velocity vector is Vx and the vertical component is Vy. So the velocity vector itself is got by completing this parallelogram. Just add these two vectors by the parallelogram law. So here is V. So at this instant in the object's motion, its velocity is in this direction. But gravity is always acting. The object has an acceleration which is in this direction. The magnitude of the acceleration is 9.81 meters per second squared. Now here we have the trajectory of the particle after completing its motion. The dots indicate the distances swept out in equal time intervals. So the time taken for the object to go from here to here is the same as the time taken for it to go from here to here, is the same as the time taken for it to go from here to here, and so on. And it's equal to the same as the time taken for it to go from this point to this point here. Let's consider the object when it was at this position here. Its velocity vector will be tangential to the trajectory. So the velocity vector will be in this direction. It has two components, Vx and Vy. So Vx is this component, and Vy is this component here. So we could add these two vectors by the parallelogram law to get vector v. A very important point when considering projectile motion is that there is no force acting on the object in the x direction. We are ignoring air resistance. There's always a bit of air resistance. Pretend there is no air. Pretend the object is being launched in a vacuum. So if there's no force acting in the x direction, then by Newton's first law or Newton's second law, the acceleration of the object in the x direction, ax, is zero. Newton's second law says that the resultant force on an object is its mass times its acceleration. But we're interested in the resultant force in the x direction, or the x component of the resultant force on the object. By Newton's second law, that's equal to the mass of the object times the x component of the acceleration of the object. But if the x component of the resultant force is zero, then we have 0 equals m times ax. In other words, ax must equal 0, because m is not 0. So the only way to get 0 is if this is 0. So that's a very important point. So if the acceleration of the mass in the x direction is 0, that means that the x component of the velocity never changes. In other words, Vx is constant. So as you saw in the applet, this vector is constant. It points in the same direction all the time, and its magnitude stays the same. Okay, it does move around, of course, but it moves around parallel to itself as the object moves. Its direction and magnitude remain the same, so it's a constant vector, Vx. Now we know from linear motion that V equals u plus at. This is linear motion with constant acceleration. Well, we can look at the x component of the motion of this object. We can look at Vx. So we can apply this formula in the x direction. So Vx equals the initial x component of the velocity plus ax times t. But we know that ax is 0, so we just get ux plus 0 times t. So we see that v of x equals u of x. So if we know the x component of the initial velocity, that is the velocity of the particle when it was launched, then we know that then we have Vx, because Vx is just equal to ux. So the particle was launched with a certain velocity. It was actually 55 meters per second. And if we want to get the x component of it, which we call ux, u is normally used for initial velocities, we just get the component of this velocity in the x direction. We have this angle in here, it was 60 degrees. So we see that ux is the hypotenuse of this right angle triangle, which is 55, multiplied by the cos of 60. We get 27.5 meters per second for ux, so that means that Vx, the x component of the velocity of the object at any point in its trajectory, is 27.5 meters per second. Now what about Vy? Now again we can consider linear motion in the y direction. So we can treat the motion of this particle as a combination of linear motion in the x direction, Vx, and linear motion in the y direction. So we apply this formula from linear motion with constant acceleration. The acceleration is actually constant, we'll see it in a minute. We apply this formula in the y direction. Now, uy we can find. Uy is this vector here, the y component of the initial velocity. Uy is the hypotenuse of this triangle, which is 55. It's the magnitude of the initial velocity. This vector here would be called u. Vector u is 55 meters per second at an angle of 60 degrees to the horizontal. That's vector u. So uy is 55 times sine of 60 degrees. uy is the side opposite 60 degrees. The sine of 60 is 0.866 to 3 decimal places. In short form, it's actually root 3 over 2. We multiply this by 55. So to 1 decimal place, we get 47.6. Now that's uy. What about ay? Well, we looked at the x component of the acceleration of this object. We saw that it was 0 because there are no forces in the x direction. So if the x component is 0, the acceleration must be entirely in the y direction. And we've explained this before. The x component, the y component of the acceleration is 9.81 meters per second squared. That's the magnitude of this vector here. So the acceleration is entirely in the y direction. Here's the acceleration. It normally has two components, x and y, but the x component is 0. So the acceleration is entirely in the y direction. And its magnitude is 9.81. However, we've got to consider directions here. We are assuming that upwards is positive. So vectors pointing up are positive vectors, so the sign gives the direction. So Vy is a positive vector. Well, it depends actually. It's positive when the particle is going from its launch position to the maximum height, and then Vy becomes negative as it falls back down to Earth again. However, A has constant magnitude, but it's pointing down the way. So we have to give it a minus sign. Uy is a positive vector. You can see that Uy is a vector pointing in the positive direction. You see, we are dealing with vectors here. So, well, vectors in one dimension. So upwards is positive, downwards is negative. So Vy equals Uy, which is plus 47.6, plus Ay, that's minus 9.81, times T. This minus sign is important because if you put a plus sign in here, it means that Vy keeps on increasing as T keeps on increasing. So normally T is naught when we launch the particle. So as T keeps on increasing, Vy does not keep on increasing, of course. So that's why we have to have a minus sign here. So at T equals naught, Uy is 47.6, but as time goes on, this number will decrease because of this minus sign, and that's what we want. So the force pulling the object to the Earth causes the y component of the velocity to decrease, and it will decrease to 0 when the particle reaches its maximum height above the Earth. At this position, Vy is 0. Here we see the particle at the highest point in its trajectory. When it's in this position, its velocity v is entirely in the x direction. So the velocity v is equal to vx. Vy is 0. And we know that vx is 27.5 meters per second. So this is the key fact for finding the highest point of a particle in its trajectory. We put Vy equal to 0. So here is Vy, we set it equal to 0, we solve for the time. So we will have the time taken for the particle to reach the highest point in the trajectory. So T is 47.6 divided by 9.81. So we get approximately 4.9 seconds. Now, a natural question is to ask, how high does the particle reach? So what is the height of the particle when it is at its maximum height? To get the maximum height, we can use this formula here. This formula is used for linear motion with constant acceleration. So we can look at the y component of the motion of this object. We are interested in finding Sy, but Ay is constant. You see, we can actually use this formula. Ay we know is minus 9.81. Uy is the y component of the initial velocity, and Sy is the position of the particle. It's just y basically. We could just call it y. So we covered all this in uniform linear motion. Uy is 55 times sine 60. Ay is minus 9.81, so a half of Ay is minus 4.9. So we're dealing with vectors here essentially. Uy is a positive vector, but Ay is a negative vector. It's pointing downwards. So if we want to find the height of the particle at any time t, we can just plug in for time and work all of this out. Sy is the height of the particle, or the y value of the position of the particle. So in particular here, we want to find the height of the particle when it reaches its maximum height. We want this distance here. We know the time taken for it to reach its maximum height, 4.9, so we just plug 4.9 into this. Working this out, we get 115.7 meters. By the way, it's a coincidence that this 4.9 happens to equal this 4.9 here. Another natural question to ask is, what is the range of the particle? So, what's this distance here? The horizontal distance from the launching pad to the point where the particle strikes the ground. Well, we notice that when the particle strikes the ground, its height, Sy, is 0. Well, it's also 0 when it's launched, of course, at the instant it's launched. So what we do is we put Sy equal to 0 and solve. So Sy equals Uyt plus a half Ayt squared. So this is just the formula for linear motion with constant acceleration in the y direction. The acceleration in the y direction is a constant minus 9.81 meters per second squared. So we just set this equal to 0. And then we can solve for the time. Uy, we know, is 55 sine 60. A half of minus 9.81 is minus 4.9. Now we solve this for time. We can factorize t out of this expression. So this is a quadratic equation. We have the two factors of it. The two factors multiply to give 0. The only way that can happen is if either of them is 0. Either t is 0 or this other factor is 0. If we put this other factor equal to 0, what do we get? I'll just write it down first. 55 sine 60 minus 4.9t equals 0. So t equals 55 sine 60 divided by 4.9. So there are two solutions. At t equals 0, Sy is 0. Well, that's no surprise, because at t equals 0, the particle has just been launched. So if it's just been launched, its height is 0. Sy is 0. And at this other value, t equals 9.7 seconds, its height is 0. So it must correspond to this position of the particle. An interesting fact is that the time of flight of the particle, that's what this is. Time of flight means the time taken for the particle to hit the ground, is twice the time taken for the particle to go from here to its maximum position. This is 2 times 4.9. We got 4.9 the last time, but because of rounding error, we don't get exactly half of this. But this number here should be half of this number. So the time taken for the particle to reach its maximum height should be half the time taken for the particle to go all the way and hit the ground. That time is sometimes called t-flight, the time of flight. By flight we mean the particle in flight for the entire journey, not just for half the journey when it hits here. So the trajectory itself is not just symmetrical in space, but there's also a symmetry in time. Let's look at the motion of the particle again. We will show the x and y components of the velocity. See the Vx component remaining constant, Vy is shrinking to 0 when it reaches its maximum at 0. Vy is now changing direction and increasing, but Vx is constant. We can show vertical lines here to indicate that the particle covers the same horizontal distances in the same time, because Vx is constant. So the time taken for the particle to go from here to here is the same as it does from here to here, and from here to here, and so on. It sweeps out equal distances in equal times in the horizontal direction, but not in the vertical direction. We can show what happens in the vertical direction. Now, these horizontal lines are not equally spaced because Vy is changing.